We determined previously that we wanted to have the second moment of inertia and the value of Q, the first moment of area, in order to do our calculations for the calculated theoretical strain values. So we have this shape for our cross-sectional area. We can use the parallel axis theorem for our second moment of inertia. We're very fortunate in this case because this AD squared term can be made to go to 0. We can take, as for the rectangle of the entire area, we can have it be, it's 1/12 base, which in this case is going to be the width of the flange, BF, times height, which in this case is D, the depth of the beam, cubed. And then we can just subtract out the second moment of inertia of this area and this area right here. And so we needn't get the AD squared term involved at all. We can keep D to be 0, because this D is the distance from the centroid of portions, the individual portions we're considering, to the centroid of the total cross-section. This D is the depth of the beam. They're not the same D. So we can subtract 1/12. In this case, the width will not be the full width. It will be the full width minus the width of this flange, which is given. And we'll multiply that by the depth, which will be D minus 2 of them times the thickness of the flange. That's also given. And then we'll cube that. And that'll be our second moment of inertia. Now, when we're considering the shear strain, which we'll get from the inputs at 1 and 2, those strain gauges are located at the neutral axis. So when we're considering Q for that, we're going to need to cut at the neutral axis, and we're going to have to consider all the area above the neutral axis for our first moment of area calculation. All of that. So we're going to do that. Q is A times Y. The way I would do this, I would break this up into 2 pieces. One rectangle right there with the centroid right there, and one rectangle right there with the centroid right there. So that will give us the thickness of the flange times the width of the flange, will be the area of the flange, it turns out, times 1/2 the total depth minus 1/2 the thickness of the flange. Right, for the centroid of this to the neutral axis. To that, we add, starting a new line here, this, which will be the thickness of the web times 1/2 of the depth minus the thickness of the flange. So just this is our area. And the distance to the neutral axis of the centroid of this is going to be D over 2 minus thickness of that, the full thickness of the flange, and then we're going to divide that by 2 because it's only 1/2 of that. So So that'll be our y value for that. The sum of those two things will give us the total Q that we need